This video is all about hypothesis testing and confidence intervals when we're looking at two samples. So we want to compare two populations and see if they're different, or one is bigger or one is less, or how much bigger or how different or how less. And we'll start out with proportions. So we'll say if we have two population proportions and we want to compare them, and we have samples, then we can conduct a hypothesis test. We can also find a confidence interval for the difference between two different population proportions. Then we're going to move on to means. Means are a little more complicated, so there isn't just two means. So independent samples mean that if you look at the data, there isn't some pairing like the very first data value for the first sample and the first data value for the second sample. They're not paired or anything. Whereas with dependent samples, they are paired. So they might be the first and second sample could be the answers to two survey questions at which you ask the same people. Or it might be the, say, temperature in two different towns on the same days that you looked at. So they would be paired. So let's start out by looking at proportions. And in particular, how do we conduct a hypothesis test for two population proportions? It turns out if you do want to conduct a hypothesis test to compare two population proportions, it's very similar to one proportion. Now, if there's two proportions, there's two sample sizes. There's an N1 and an N2, and there'll be two sample proportions, a P1 and a P2, and also two proportions of no answers, a Q1 and a Q2. So instead of just NP and NQ needing to be greater than 5 to continue, we need to make sure that N1P1, N2P2, N1Q1, and N2Q2 are all bigger than 5. So that means the number of yes answers for both the first sample and the second sample, or at least the expected number if it's a hypothesis test, then the number of yes answers must both be greater than 5, and the number of no answers must both be greater than 5 for both samples. The other thing is the conclusion is not about a population proportion, it's about two different population proportions. So you might be 95% confident that this population proportion is bigger than the other population proportion by between these two numbers. Or you might be able to say there's statistically insignificant evidence to show there's a difference between the two population proportions. So for confidence intervals in particular, often, again, we use a 95% confidence level. That's standard, but you could go higher or you could go lower, similar to one sample. And it means that if many studies are conducted, then each would produce its own confidence interval for the difference between the two. Very similar to what we did before, but now we're talking about differences. 95% of these confidence intervals will contain the true population difference between the two proportions, and 5% will not. Really similar to what we did before, but now we're just talking about a difference between the two population proportions instead of just what is the population proportion. So if they're both positive or both negative, then if we have a 95% confidence interval being A to B, and they're both positive or both negative, then with 95% confidence, it can be concluded that the first variable is between, and then you can compute it. So if it was, say, 0.3, then you would say 30%. So 100 times A%, and 100 times B%. So if B were, say, 0.51, that would be 51%. More or less likely if it was negative. to occur than the second variable. And we'll have some examples of how to interpret these. If they're different signs, so if you conduct a study between two different proportions and you find a confidence interval, in particular 95% confidence interval, say, where you get A to B, and A is negative and B is positive, then with 95% confidence, we don't know which proportion is higher. If A is negative, then that tells you the first is smaller, whereas if B is positive, that tells you the first is larger. It's always the first minus the second, by the way. So we often say that the results are within the margin of error. Okay? Now the A and B do have meaning. Let's say A is negative 0.00003 and B is positive 0.00001. Then yeah, we don't know which one's bigger, but we can say they don't differ by much because A and B are both really close to zero. So that's just some notes about confidence intervals. So now for hypothesis testing. When we had one sample, we understood how to compute and how to interpret the p-value. So for a one-tailed test, for example, if a left-tailed or right-tailed hypothesis test results in a p-value of, let's say, 0.03. And let's say the sample difference between the proportions was 8%, for example. Then if H naught is true, and another study was conducted with the same sample size as the current study, then there is a 3% chance, that's our p-value, that the new study will result in the first proportion being at least 8% less, because we have 8% here, or if it's right-tailed, more, than the second proportion. So when you're computing the p-value, you're talking about not what is the probability of this number or this proportion being bigger than something. It's really we're comparing the two. We're saying what's the probability of the first being at least this much bigger than the second, or smaller, depending on the tails. Okay, to interpret the level of significance, very similar. If a hypothesis test results in H naught rejected with a 5% level of significance, then if H naught is true, and another study was conducted with the same sample size as the current study, then there is a 5% chance that the null hypothesis would be rejected, even though the null hypothesis is true. That would be if you're using a 5% level of significance. Very similar to what we did with single samples, but now we have two samples. So not really much different. It's if the null hypothesis is true, it's the probability of ending up going, uh-oh, I found out it was false, that was my evidence, and you weren't right. So that's called a type 1 error. So nothing different than before. Okay, so if you have a two-tail test, then let's suppose you had 0.03, and let's suppose the sample difference between the proportion was 8%. Again, whatever you get will be different than that. Then if H naught is true, and another study was conducted with the same sample size as the current study, then there is a 3% chance, that's the p-value, that the new study will result in either the first proportion being at least 8% less than the second proportion, or the first proportion being at least 8% more than the second proportion. Another way of saying that is there's a 3% chance that the two proportions will differ by at least 8%. And that's how you interpret the p-value when you have a two-tailed test. All right, let's take a look at an example. So here's the example I've got. Our transfer students from community colleges more likely to major in the health sciences than students who go directly to a university from high school. Might be true, might not. Let's see. Let's conduct a test. Let's do a survey. So let's suppose that we survey 200 community college transfer students, and 42 of the 200 community college transfer students surveyed had majors in the health sciences. And let's suppose we also asked 300 students who came directly from the high school. And 50 of those 300 direct students had majors in the health sciences. What can be concluded at the 5% or 0.05 level of significance? Also, find a 95% confidence interval for this difference. So let's first figure out what the hypotheses are. As you're used to, there's going to be an H naught and there'll be an H1. So let's find those. So H naught is that the proportion of all students, so the population proportion of all students that transfer from community colleges, is equal to the population proportion of all students who transfer right from high school or come to the university right from high school. H1 is that the population proportion of university students who transfer from a community college and want to major in health science is greater than the population proportion of students who came right from the high school and major in the health sciences. Notice greater than because we're asking if community colleges are more likely to major in health sciences. More is greater than. Then we should look at all these numbers: 42, 200, 50, 300, 0.05, and 95%. And let's write down what they are in terms of symbols. So the 42, that was, I'm going to call that X sub C, the number of community college transfer students who said yes, is 42. NC, that was our sample size for those who transferred from the community college, that was 200. X sub U, that was the number of direct university students who majored in health science, that was 50. And N sub U was 300. We want a 95% confidence interval for the difference. So CL, confidence level, is 0.95. Now we're ready to go to our calculator to come up with the p-value and the confidence interval. So let's do that. Here's the calculator. I'm going to scroll a bit, and I want two proportions. So right here, number 19, it says two proportions. I click on that, and it asks for the sample size for the first sample. That was 200. It asked for the number of successes for the first sample. That was 42. It asked for the sample size for the second sample. That was 300. And it asked for the number of successes for the second sample. That was 50. It asked for what tail test we have. We had a greater than. And it asked for CL, the confidence level. That was 0.95. I hit calculate, and it gives us everything we need. So notice the p-value is 0.11. 0.11 is high, and in fact, it's higher than the level of significance of 5% or 0.05. Remember, when the p-value is large, you fail to reject the null hypothesis, and there is insufficient evidence or statistically insignificant evidence. No different than what we had for one sample in terms of understanding the p-value. The lower bound for the confidence level is 0.03 or so, or 0.026. And the upper bound is about 0.11. So notice we have a negative and a positive. So sometimes we'll say it's within the margin of error, but we're going to interpret the two numbers, how much bigger one is than the other. We can say that they're not that far away from each other. So now let's actually do the formal interpretation. All right, we had a p-value that was much bigger than the 5%. So we can conclude that there is statistically insignificant evidence. When the p-value is high, we get insignificant evidence to conclude that the population proportion, notice we're not talking about the samples, we're talking about the entire population of all community college students and all students that come right from the high school. So the population proportion of transfer students from community colleges who major in the health sciences is greater than it is for students who go directly to a university from high school. So notice that by saying it's statistically insignificant, this is just a fancy way of saying we don't know anything. So that is the interpretation, or that's the conclusion for the hypothesis test. So now let's talk about the confidence interval. And we can state with 95% confidence the population proportion of transfer students from community colleges who major in the health sciences is between 3% lower and 11% higher, because that was a lower bound, if you remember, was negative 0.03 or so, and the upper bound was 0.11 or so. So between 3% lower and 11% higher than the population proportion of students who go directly to a university from high school who major in the health sciences. Okay, so now let's look at another example. So the next example is the following. Are Democrats less likely to own an American car than Republicans? I'm not sure. Maybe, maybe not. Of the 150 Democrats surveyed, 65 of them owned an American car, and 120 Republicans surveyed, 70 owned an American car. What can be concluded at the 0.05 level? Also find a 95% confidence interval for this difference. So, just like before, we need to write down the null and alternative hypotheses. So the null hypothesis is H naught colon P sub D, that is the population proportion of Democrats who own an American car, is equal to P sub R, or the population proportion of Republicans who own an American car. Now H1 colon, the alternative hypothesis, is that the population proportion, P sub D, of Democrats who own an American car is less than the population proportion of Republicans who own an American car, because we want to see if the Democrats are less likely to own an American car than Republicans. Let's take all these numbers and write down their corresponding symbols. We surveyed 150 Democrats. 65 of them owned an American car. So X sub D is 65, and N sub D is equal to 150. And 120 Republicans surveyed, 70 own an American car. So X sub R is 70, and N sub R is 120. We want a 95% confidence interval. So our confidence level, CL, is 0.95. And as we're used to, we can jump right to the calculator. So let's do that. So here's the calculator that we had just seen, but now the first sample size was 150. The first sample's number of successes was 65. The second sample's sample size was 120. And the second sample's number of successes was 70. The alternative hypothesis was that P1 is less than P2, or PD is less than PR for Democrats and Republicans. Our confidence level is still 0.95, and I just hit calculate. And then I look, and there we have it. Notice the p-value is 0.007, definitely small enough to reject the null hypothesis and accept the alternative hypothesis. The lower bound is negative 0.27, and the upper bound is negative 0.03. Okay, so that means when you have a negative sign, that tells you the first is likely to be less than the second by that percent. So in this case, the Democrats who own an American car, that proportion, looks like between 3% and 27% less than the Republicans. So now let's state the conclusion formally. So we can conclude there is statistically significant evidence to conclude that the population proportion of all Democrats who own an American car is less than the population proportion of all Republicans who own an American car, because our p-value is so small. In fact, we could even say there's strong statistically significant evidence with such a small p-value. So now let's look at the confidence interval. We can say with 95% confidence, the percent of all Democrats who own an American car is between 27% and 30% lower than the percent of all Republicans who own an American car. Notice lower because we got negative values for our confidence interval. So that's how we deal with comparing two proportions. Now let's talk about means. So let me look at this example. Is there a difference between the amount of studying for male and female students? The 45 male students in the survey averaged 8 hours of studying per week and had a standard deviation of 3 hours. The 38 female students averaged 8.4 hours per week and had a standard deviation of 2.5 hours. What can be concluded at the 0.1 or 10% level of significance? Also, find a 90% confidence interval for this difference. Notice one thing is that it's just a bunch of male students and a bunch of female students. We're not looking at couples where we can say, well, we compare these guys up. It's just this group, and they're just two different groups. It's not a bunch of pairs. And that is important. We call these independent samples. So we need to write down our null and alternative hypotheses as we're used to. So the null hypothesis, H naught colon, is that, well, we want to see if men are the same or not in terms of the average amount of hours that they study, in particular the population mean number of hours. So we write mu sub m equals mu sub f, or the population mean number of hours that men study is equal to the population number of hours that women study, or females. And then the alternative hypothesis, H sub 1, colon, well, we want to see if there's a difference. And we're used to that when we see the word difference, that's a not equal to sign. So we could say mu sub m is not equal to mu sub f. Next, we have all these numbers. Let's gather them up. So we had 45 male students in the sample. So n sub m equals 45. Their mean was 8. So x bar sub m is 8. and their standard deviation was 3, so S sub m equals 3. For the females, there were 38 of them, so N sub F equals 38. They averaged 8.4 hours per week, so X sub F bar equals 8.4. And their standard deviation was 2.5, so S sub F equals 2.5. And the confidence level is 0.90 because we want to find a 90% confidence interval. Now let's jump to the calculator. We certainly don't want to use a two proportions calculator because we're not talking about proportions here. We're talking about means. So let's move back to the calculator menu, and I'm going to scroll a bit. And I want two independent samples with statistics. These are independent. We're not pairing people or anything. And we have statistics. We don't have data. So I click on that. It asked for the first sample size. That was 45. It asked for the first sample mean, which was 8. And its standard deviation was 3. For the second sample, there were 38 females in the second sample. Their sample mean was 8.4. And their standard deviation, the sample standard deviation, was 2.5. We wanted a not equal to. We're checking to see if they're different. And the confidence level here was 0.9. So as you're used to, I hit calculate. And look at that. We have a p-value of about 0.51. Okay, way high. And our lower bound is about negative 1.4, and our upper bound is about 0.6. With the p-value so high, we definitely fail to reject. And we have a lower bound and an upper bound. They're pretty far apart. One's negative, one's positive. So this study really didn't show much in terms of showing there's a difference. So let's write down our conclusion. So with such a high p-value, we say that there is statistically insignificant evidence to conclude that there is a difference between the population mean amount of studying for male and female students. Okay, p was way too high. We can also interpret the p-value. If you remember, the p-value is about 0.51 or 51%. And the way we interpret it is the following. We say if the population mean amount of studying for male and female students is the same, so in other words, if H naught is true, and if another 45 male and 38 female students were surveyed, that's what we had done, we surveyed 45 and 38, then there would be a 51% chance, our p-value is 0.51, so there would be a 51% chance that the two sample means would differ by at least 0.4 hours. Notice 8.4 minus 8 is 0.4. So they differed by 0.4 hours. P-value is all about if the null hypothesis is true and you conducted another study, then it's the probability that you're going to end up getting something as unusual as what you got. So that was the interpretation of the p-value. Now let's move to understanding what the level of significance is. And it's very similar to what we have done in prior chapters. And we can say if the population mean amount of studying for male and female students is the same, and if another 45 male and 38 female students were surveyed, then there would be a 10% chance, because our level of significance was 0.1 or 10%. So there would be a 10% chance we would end up falsely concluding that the population means differ. So it's always the same. If the null hypothesis is true and we did the similar study, then the level of significance is the percent chance that you're going to end up falsely concluding that H1 is true. This is the same thing as a type 1 error. So now let's talk about the confidence interval. So if you remember, our confidence interval went from negative 1.4 to positive 0.6. Negative means that the male's less than the female in the population mean hours of studying, and positive means the male is more. So we can say with 90% confidence, the population mean number of hours male students study is between 1.4 hours less and 0.6 hours more than the population mean number of hours female students study. That's how we interpret this confidence interval. What about the 90%? What does it mean to be 90% confident? Let's check that out. For this interpretation, we can say if many surveys of 45 male and 38 female students were conducted, then each would result in a different confidence interval. And that's a confidence interval for the population mean difference. 90% of these confidence intervals will contain the true difference in population mean study hours between male and female students. So next, we can talk about difference between means with another example. So here it is. Are tips better on Saturdays compared to Fridays? So if you are in the wait staff at a restaurant, you hope you get lots of tips. And, people are supposed to tip more than 15%. What are they really tipping? Okay, a waiter looked at 32 tips from Fridays and found the mean to be 18%, and the standard deviation was 2.5%. For the 35 Saturday tips, the mean was 20%, and the standard deviation was 3%. What can be concluded at the 0.05 level of significance? Also find a 95% confidence interval for this difference. So as you're used to, we need to start out with the null and alternative hypotheses. So for the null hypothesis, we want to show the population mean. Again, it's the mean tip that this waiter's getting. So H naught is that the population mean tip on Fridays is equal to the population mean tip on Saturdays. H1, well, we're thinking Friday is less. So the population mean tip on Fridays is less than the population mean tip on Saturdays. Mu sub f is less than mu sub s. Then let's write down what all these numbers are. We have the number for Friday, the sample size for Friday was 32. The X bar for Friday, the sample mean for Friday, was 18. The sample standard deviation for Fridays was 2.5. The sample size for Saturday was 35, so n sub s is 35. The sample mean for Saturdays was 20. The sample standard deviation for Saturdays was 3. And our confidence level, our CL, is 0.95. So now we're ready for the calculator. Okay, we're still in the calculator, and we're still looking at two independent samples with statistics, because that first customer on Friday had nothing to do with the first customer on Saturday. They're not paired or anything. So our sample size for the first sample was 32. The sample mean was 18. Sample standard deviation was 2.5. For the second sample, the sample size was 35. The sample mean was 20. And the sample standard deviation was 3. We wanted to test to see if Friday is less than Saturday in terms of the population means, so less than. The confidence level this time was 0.95. And I hit calculate. That's all there is to it. And there it is. I get a p-value of 0.002. Notice the lower bound is negative 3.3-ish, and the upper bound is negative 0.66-ish. So notice that when you have negative numbers, that means we're seeing that the first is less than the second, at least for our confidence interval. So now let's write down our conclusions. So we had a very small p-value, so we can conclude that there is statistically significant evidence that the population mean tip on Saturdays is higher than on Fridays. And then for the confidence interval, if you remember, it was around 0.66, or actually negative 0.66, and negative 3.34. When you have negative, that means that the first is smaller than the second. So we can say with 95% confidence, the population mean tip on Saturdays is between 6.6% and 3.34% higher than on Fridays. So Saturday is a better day to work for this wait staff. So now let's talk about dependent samples. Dependent samples are pretty different. So now we're looking at paired data. And what we can say is that two samples are called dependent or paired if there was a pairing between corresponding data entries of the two samples. The variables must be quantitative and subtraction must make sense. Then we can consider them dependent or paired and conduct a hypothesis test and find a confidence interval for the paired differences. So some examples are before and after studies. So you might, for example, look at some kind of treatment in the hospital, and you might want to look at the blood pressure before they receive the treatment, and then the blood pressure after they receive the treatment. And you might want to look at maybe 50 different patients. So each patient is getting tested before and tested after the treatment. This is also used in twin studies. So for example, if you can find, let's say, 50 pairs of identical twins that were brought up in different situations, maybe one in poverty and one in wealth, and maybe you want to see if the GPA is different. Well, you could look at those pairs of identical twins, look at the ones in poverty, look at the ones in wealth, and those are paired up, they're dependent, and see if there's a difference. You can compare two locations at many different times. So that might be looking at, say, the high temperature in two areas, maybe in California, to see if there's a difference between the high temperature. And you look at maybe 50 different days of the year and look at the high temperatures for those two locations. That would be paired or dependent. Also, answers to two survey questions. So a lot of times you can have a survey, and that survey might have two different questions where the variables are quantitative and comparable. So that might be something like, how many calories do you eat for lunch? And how many calories do you eat for dinner? And to see, well, people maybe eat more for dinner than lunch. So notice if you asked 100 people those two questions, then each person has two different answers. So they would be paired, and those would be dependent. So let's look at an example. A study was done to see if Heavenly receives less snow on average than Kirkwood. These are two ski resorts in Tahoe, and some people like one better than the other. Some people think Kirkwood's a lot better. So let's see. The snow amounts in inches received for the 8 randomly selected storms was tabulated. What can be concluded at the 0.05 level of significance? Find a 95% confidence interval and assume a normal distribution. And we're given the data that was collected on 8 different days for both Heavenly and Kirkwood for those days at which there were storms. And these are the inches of snow that happened in those 2 ski resorts. We want to find out, does Heavenly receive less? So notice these are paired because for each day, we have 2 different values. We have Heavenly's value and Kirkwood's value. So this 10 and this 11 were from the same storm, and that makes them paired. So for this one, we have the data, and now we can go to our calculator, and we can pop in the data and come up with the p-value and the confidence interval for the difference. So here's the calculator, but this is the 2 independent samples. With statistics calculator, we don't want independent samples. We want dependent samples, and we don't have statistics. So let's go ahead and go back to the calculator. And let's go find what we need. And we will see 2 dependent samples with data. And I click on that. And it asks to put the data 1 and data 2 separated by commas. So I'm going to do that. And I didn't want to waste your time, so I just put in the data right now. And here were the data for data 1, and here's the data for data 2. Those are the 2 rows of that table. So for this example, we have a less than, because we want to show that Heavenly, or we're thinking that Heavenly has less snow on average than Kirkwood for the average storm. The confidence level was 0.95. And I hit calculate. And here it is, 0.007 or so, very small. So it looks good. It looks good. I do want to note something, a couple things. One is that our sample size is very small. So that assumption that everything is normally distributed, that means that the differences are normally distributed. We need that assumption, and it may or may not be true, so be careful. So the recommendation is never do a study so small, get more data values. Okay, so this is maybe not true, but we'll do our best for this example. Notice that I wrote down in the calculator, or the calculator gives us, the data diff. So these are the differences in the data values, the first minus the second. And you'll notice that we end up with a single sample of differences. And it turns out we're just doing a t-test for the differences, just like we did in the prior chapter. The lower bound for the confidence interval was around negative 9.7 or so, and the upper bound was negative 1.55, etc. And when it's negative, that means the first is likely to be smaller than the second. So now let's go and interpret. So we had H naught was at mu sub d equals 0, because the means were the same, and H1 was at mu sub d is less than 0, because we want to show that Heavenly has less snow on average for the storms than Kirkwood. And we had a p-value that was very, very small, so that means that we can conclude that we have statistically significant evidence that H1 is true. Or, in words, there is statistically significant evidence to conclude that the population mean snowfall at Heavenly is less than at Kirkwood. And for the confidence interval, remember we had negative 9.7 to negative 1.6. I like to take the negatives out and turn the greater than into a less than and switch the order. And here's how I like to interpret it. With 95% confidence, the population mean snowfall that Heavenly receives is between 1.6 and 9.7 inches less than what Kirkwood receives. So Kirkwood looks like receives more snow. Let's look at one more example. So here we have it. 9 people were tested for memory recall before and after drinking a shot of whiskey. The table below shows a number of digits they could recall for this before and after study. So maybe they were each given a bunch of numbers and they were asked maybe a minute later, Tell me what those numbers were and how many numbers could they remember. Is there evidence at the 5% level of significance that memory is reduced after drinking alcohol? Find the 95% confidence interval for the difference. And here's the before and after data. So we do very similar to what we did before. Notice, by the way, that our H naught is that mu sub D equals 0. The mean difference is 0. Because if they're the same, you subtract them, you should get 0. And H1 is mu sub D is greater than 0. Because our hypothesis is that if you drink alcohol, then you're going to remember less. So that means before is greater than after. Just another big note, another small sample size, warning, 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 warning. Small sample sizes are dangerous. We can only do this if we assume we have a normal distribution for the before minus after differences. And I have no idea whether that's normal or not, but I'm going to make that assumption. In the real world, I would survey a lot more people than just this number. So let's go to our calculator. Here's the calculator again, and we're still in the situation of two dependent samples with data. So I don't have to change calculators. I can use the same one I just used. And I spared you the time, and I typed in the values for data 1, the before values, and I typed in the values for data 2, the after values, separated by commas. We want to hypothesize that the first is greater than the second. People remember more before they drink than after they drink. And we still want a 95% confidence level. So 0.95 for CL. And hit calculate. That's all there is to it. And here we have a p-value of 0.09-ish. Our upper bound is negative 0.58, and our lower bound is 2.58. So now we can go back and interpret what's going on. Notice if we want a 5% level of significance, 0.09 is too big. That means we're going to fail to reject the null hypothesis. So let's check it out. So for the hypothesis test, we had a p-value that was too big. So there is statistically insignificant evidence to conclude that the population mean memory recall is lower after drinking a shot of whiskey compared to before, which is the same thing as higher before compared to after. Either way you say it, it means exactly the same thing. Notice, by the way, that does not mean that you don't lose memory after you drink. Our sample size was tiny. When your sample size is tiny, you should always worry about especially a type 2 error. So we may have a type 2 error here, which meant that we had insignificant evidence, but it really was true. We just don't know because the sample size is too small, basically. Okay, or maybe we didn't have a type 2 error. Maybe it doesn't make a difference. We really just don't know. And that's all you can say when you have a large p-value. Now let's interpret the confidence interval. Notice we had a negative 0.6 and a positive 2.6. When it's negative, that means the first is less. When it's positive, it means the first is more. So we can state with 95% confidence, the population mean number of digits people can remember before taking a shot of whiskey is between 0.6 less and 2.6 more than after taking a shot of whiskey. So that's the last example that I have for this video. And hopefully this made sense. You want to practice, practice, practice. And if you have any questions about confidence intervals for the difference between two means or proportions, or any other questions, and if you're my student, please ask me. I'll be happy to answer. If you have a different instructor, please ask your other instructor, and I'm sure they'll be happy to answer also. So thank you for watching this video.